What I want to talk about today is Bushong chapter 2. And in Bushong chapter 2, what he goes into are basic principles of physics. Starts off with basic math, and we'll talk a little bit about that, but I'm not going to spend just a tremendous amount of time talking about basic math. The reason for that is because most of you have been through some sort of math class in college, and certainly you've had math for your academic career in high school. So we'll talk a little bit about it, but then we'll talk about the basic physics. And it would appear on surface like most of what we're going to talk about today doesn't have anything to do with radiology, but it does. So what I'm going to do is I'm going to describe the different physical principles that are covered in Bushong chapter 2. But then I'm going to tell you how they apply specifically to radiologic technology and X-ray creation. So in as much as what you've seen in clinicals and what you've learned about in positioning, it doesn't have a whole lot of application, but it does have application in creation of the X-ray beam, and that's where we're going to spend a lot of this semester. I want to alleviate some fears. So if you're looking at chapter 2 and you're looking around page 28, you see a lot of very complicated formulas like average velocity, there's acceleration, there's Newton's 3 laws, including force, which is a mathematical equation. There's, on page 27, there's velocity, which just means speed. On 30, there's momentum, there's work, there's power, there's energy, kinetic energy, potential energy, all these different mathematical equations that seem like they're very complicated, and they kind of are. To a degree, anyway. But I'm going to try to simplify them the best I can. And to answer the question, you're probably thinking you're not going to have to work any of those on my test. They're not things that are going to show up on the registry. And I try to keep my lectures and my expectations in class geared towards what you might run into on the registry, also on my tests as well. So the things that we're going to talk about are going to be in context of describing those formulas and not necessarily in how you have to work them. You have to know the components and the different things that go into the formulation of the formula itself, but in as much as having to work those formulas, I'm not going to hold you responsible for that. So you have to be able to pick it out from a description, know the components in it, and then answer a multiple choice question about that particular formula, but you're not going to have to work them. So let's just start with basic math. Where things get complicated in basic math is not with your basic addition, subtraction, multiplication, and division. Those are pretty straightforward. But once we throw in fractions and decimals, they tend to cause some problems and some anxieties. So just to simplify fraction is just basic division. It's the numerator divided by the denominator. And decimals are just a type of fraction. It's the fraction is it's a percentage, or it's a tenth or a fifth or something like that of a whole. So a fraction and decimal both are just a portion of a whole. So you can convert fractions to decimals, you can convert decimals to fractions. Conversion of fractions to decimals, very simple. On all of my tests, you can use a basic function calculator, and we've got a drawer full of those in our classroom. You can't use a programmable calculator, but you can use a basic function. If you have a basic function that is your good luck charm or whatever, it's one of those big square things that you want to carry to class, that's fine. It just cannot be programmable. So conversion of fractions to decimals is just a division of the numerator by the denominator. So a half would be equivalent to 1 divided by 2, which would give you a decimal of 0.5. And you can do that on your calculator. Just put in 1 divided by 2, and that's going to give you 0.5. Decimals to fractions is a little bit more complicated, and you're probably going to have to use a pen and paper for that, but just write out the decimal, like 0.5 is the same thing as 5/10, but 5/10 is a improper fraction. So you need to divide both by 2. So, or I'm sorry, both by 5. So what that would give you is 1/2. So 1/2 and 0.5 really mean the same thing. So it gets a little bit more complicated when you're adding and subtracting fractions. So what you need to do when you add and subtract is the first thing you need to do is find a common denominator. And sometimes common denominator, the easiest way to get to it is just to multiply the two denominators. And sometimes that's unnecessary. Like if you have 1/6 and 1/12, then 12 or 6 being a half of 12, then you could convert 1/6 to 2/12ths. That would mean the same thing. So, but if you're really in a jam, you can just multiply the two together to find your common denominator. Like in this case, we have 1/2 and 1/3. So 2 times 3 would be 6. So your common denominator would be 6. But you have to go back and you have to convert the numerator as well. So 1/2 would equal to 3/6. And 1/3 would equal 2/6. So then you've got a common denominator and you can just add the numerator. A common mistake people make, aside from not finding the common denominator, is then adding the numerator and the denominator. And that's not what you're going to do. You're just going to add the numerator and the denominator remains what the denominator was. So 3/6 plus 2/6 does not equal 5/12ths. It equals 5/6. Subtraction is just the same thing, essentially 1/2 minus 1/3 equals 3/6 minus 2/6, and that will give you 1/6. So it gets really multiplication of fractions is really not all that difficult. Multiplication would just be straight across. 1 times 1 equals 1, and then 2 times 3 equals 6. So 1/2 times 1/3 would be equivalent to 1/6. With division, though, you set it up kind of like multiplication, but instead of multiplying straight across or dividing straight across, what you would do is cross multiply. So 1/2 divided by 1/3 would be our division problem here. So it would be the same as 1/2 times 3 over 1, and that would give us 3 over 2, which is an improper fraction, and so that will be 1/2. Whenever we're adding decimals, it's really important to line up that decimal for whatever decimal points you're adding. So if you're adding together, let's say 0.1 and 0.01, then line up the decimal point, and then it's just straight addition. So that would be a 0.11 is what those two added together would be. So that's addition and subtraction with multiplication. What you have to do with multiplication is you multiply the numbers, but then you count the places to the right of the decimal. So you've got 0.1 times 0.1. So as 0.1, we've got one place to the right, and we've got one place to the right. So together that would move the decimal place two places to the left, and we'd have 0.01. Algebra is something that scares students to death. Some of you have had a college algebra, and that's going to be helpful for you in this semester, and also subsequent semesters, because we're going to use algebra. And you use algebra all the time. You just don't really know that you're using algebra, so it's not as scary as what it seems like it would be. But it's kind of like a word problem. You use it all the time. So let's say in this scenario you have $20. You got $20, and you want to buy as many tacos as you can. The tacos are $4 each. They better be good tacos, $4 each, but they're $4 each. How many tacos can you buy? Essentially what you're setting up there is an algebraic equation. You're solving for the unknown being how many tacos you can buy. So the cost of the tacos is $4, number of tacos you can afford, we're going to say T. We're going to call that T. Most of the time you use an X, but I didn't want to confuse you with 4 times X, so I use T. So your budget's $20, so 4 times T, T being the number of tacos that you can buy, equals 20. So how do you solve for that? Well, you got to isolate that T. So you divide both sides by 4, and that gives you t equals 5. You can buy 5 tacos for $20. Exponents are just a way of taking a massive number and making something that's a little bit more, it's easier for you to wrap your mind around these extremely large numbers. So I like to use the example of amperage. So we use one of our technical factors is amperage. So whenever we're setting up our X-ray machine, we set our kilovoltage and we set up milliamperage. Kilovoltage means thousands of volts. Milliamperage means thousandths of amps, right? So what we're doing then is whenever we make an exposure, whenever we push the prep button, what we're doing is we're spinning the anode for reasons we'll talk about later in this chapter and more later in the semester, but we start to spin the anode. That's your rotor. So you rotor up, covered that in the last video, you rotor up, but at the same time you take electrons and you congest them on that filament, and that creates a space charge or an electron cloud. It creates what we call thermionic emissions. They're all electrons, so they're ions. So therm, heat, hot, ions. Hot ions, we're collecting hot ions around the filament. And that's just because we're congesting a lot of electrons on that little bitty filament. When I get into class, I'm going to show you what the filament looks like. It's basically like a light bulb filament. It's just very small. So if we were to make a 1 amp exposure, then would be a massive exposure. But what that would mean is that we would use this number of electrons. So I don't even know what that number is. It's huge. It's massive. I count the zeros and I come up with exactly what that number is. Don't care. Doesn't matter. Not going to do it. So in exponential form, it's just a little bit easier to look at. It doesn't have all these intimidating zeros behind it. It just doesn't look all that big. So the amperage we use though is milliamps, which is thousandths of amps. So if we made let's say an exposure on a patient's finger, we might use a 1 mass exposure. So 1 mass exposure would be 1/1000th of all this, right? So how we would then represent the number of electrons that we create or we have in our thermionic emissions is to divide this by 1,000, which seems like it'd be a big process to set up a division formula with this number, and it absolutely would. So really, the only thing that you have to do then in exponential form, if you're looking at a division problem, is to count the zeros, right? So there's 3 zeros in 1,000, so you're just going to knock 3 zeros off of this number right here, and suddenly this is what your number becomes. So in a 1 mass exposure, if you're doing a finger or a hand and you use a 1 mass exposure, what you're running through your X-ray tube is that number of electrons. It's a massive number of electrons. I think I touched on the inefficiency of X-ray creation. And X-ray creation is just a numbers game. So only about 1% of the electrons we send across the X-ray tube that smack into the anode become X-rays. So only about 1% of the electrons, I think I said X-rays, but about 1% of the electrons that go across the tube and smack into the anode become X-rays. Only about 1%. So out of all these electrons we're going to send across the X-ray tube, only about 1% become X-ray photons. And even if only about 1% of those are useful X-ray photons, because if you remember from the last lecture where we were talking about X-rays being created and having to be filtered out so that it made the X-ray beam safer. Incidentally enough, we refer to that as hardening the X-ray beam. You want to file that away. Hardening the X-ray beam means removing low energy X-ray photons that aren't going to make it to the image receptor and contribute to the image anyway. So let's say in this scenario, we've created this many electrons for a 1 mass exposure. only 1% of those become X-rays, and of those 1%, only 1% become X-rays of use. Okay, so let's walk through that. So we've got this many X-rays in a one mass exposure. So 1% of something, 100% of something is the whole, right? So 1% of something would mean that we're at 1/100th of our whole. So we'd have to knock 2 zeros off. So if only 1% become X-rays, we've got to knock these 2 zeros off. If only 1% of those are useful X-rays, we've got to knock these 2 zeros off. But we still have a tremendous number of X-ray photons that we're going to create. So then our overall X-rays would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it'd be 6.24 times 10 to the 11th power X-rays that we get off of this one mass exposure. So in a real life situation, are you ever going to use that? And the answer is no. Are you possibly going to answer some questions related to exponential form on my test? The answer is potentially at some point, probably sophomore imaging. Are you going to have to answer some of those on the registry? And the answer is you very well may have to. So that's the reason we're covering it, is because you may have to answer those questions on the registry. So then finally we get into our basics of physics. So this is a primer of physics, and it really kind of picks up on page 22. So a number system, our decimal system, base 10 system, you're not going to have to calculate the U.S. debt, which is well above that, and it's quite depressing at this point. So we're going to pick up with, graphing. We're going to zip past graphing, and we're going to talk about standard units of measurement on page 24. So we've basically got 3 standard units of measurement. That would be length, mass, and time. And we're going to talk about each one of those individually. We've also got special units that we talked about at the end of the last section. Special units that we use in radiography would be your things like your Gray, your Sievert, your Kerma, and your Becquerel. Again, old terminology, and what we used to call those things were not necessarily in the same order. Rad, Rinkin, Rim, and Curie. I think I failed to mention Curie. It was used because of Madame Curie and all her work that she did with radium. So just taking those individually, length, what we're going to focus on mainly is our scientific measure as far as in discussion of these different things. So our length in a scientific measure is going to be a meter. Other measures that we use frequently here in the U.S. would be a foot, a yard, inches, but really your scientific measure is going to be your meter. Your kilometer just means 1,000 meters. Centimeter means 1/10 of a meter. So centimeter is close to a half an inch, just to give you some sort of idea of how big that is. So what we used to use for the definitive measurement of length was in Paris. There was this bar of platinum iridium that had 2 marks on it, and that was our measure of a meter. But really now what we use is a wavelength of light from the isotope of krypton, and that's been ever since 1960 that we've used that. So our unit of mass is kilograms. Again, mass and weight do not mean the same thing. Weight is better measured in newtons and pounds and stone, things like that. But we do tend to think of mass and weight being the same thing, but it's just not. So 1,000 cubic centimeters of water at 4 degrees is what we use for our measurement of a kilogram. So it's not exactly the same thing as not exactly the same thing as weight. Weight is the gravitational effect on mass, even though we kind of use them interchangeably. So don't get too hung up on that. Just know for the test that they're not the same thing. But, again, if you go into the gym, or wherever that you might see kilograms represented, don't get too hung up on the difference between the two, because it doesn't really matter. But for the test and all the way through the registry, just understand they're not necessarily the same thing. So time is based on seconds, and that would be based on, or time is seconds, are seconds, and based on the vibration of cesium atoms, is extremely accurate and consistent. Your atomic clocks are based on that, that measurement of time. So whenever you buy an atomic clock or an atomic watch, or a watch that works off atomic time, then it connects to the central measurement of those cesium atoms. It's not necessarily counting cesium atoms, but it does connect to kind of a network that keeps time in that way. So those are your base units, but we also have derived units as well. And a derived unit is any unit that takes two of those base units and it joins them together, or potentially takes one unit and combines it in a couple of different ways. So there are units that, derived units, a unit that takes two different measurements. So a base unit would be a meter. A derived unit may be square cubic meters. So a meter is just a measurement of length, and it has no real volume to it. But once you say square meter, then you're talking about an area. All right. So, and if you are talking about cubic meters, now you're talking about a three-dimensional thing. So you've gone from one-dimensional without any real body to it to square meters. You've got actual dimensions, and then cubic meters. You've got three dimensions as well. So then another example would be kilometers. Kilometers per second would be a derived unit. So a base unit would be kilometers per second. Now you've got two different things going on there. You've got length, and you've also got time. So kilometers per second would be a derived unit as well. So how do measurements work? Well, we have to have two different things. We have to have a unit. A unit is what we are measuring. So is it time? Is it distance? Is it volume? Is it what is it that we're measuring? And then magnitude is how much of that unit do we have. And you got to have both of them to make sense of the quantity. I think Bushong mentions kicking a ball. How far do you kick a ball? Well, just saying 50 doesn't mean anything, but 50 yards means something, right? So kind of the same thing if you're driving to Dallas. How far is it from Tyler to Dallas? Answering 100 really doesn't mean anything if somebody is not from the Tyler area. They have no idea. Or if you say miles, they know that it's more than one because you said at the end of miles, right? So, but to say 100 miles, and that's roughly, wouldn't make a whole lot of sense to people. Even though, again, our unit, our scientific unit would be kilometers. That would be closer to, 140 kilometers. I don't know. I'd have to do the math. But don't get hung up on that either. Even though our scientific measurements are meters and kilograms, it's okay that we use something different. We just never made that conversion over. So then we get into mechanics. This is where the formulas start coming in, and it seems to get a little bit scary for students. So what we have in mechanics, we've got velocity. Velocity just means speed. Speed means how fast something is going. So the formula for velocity is V equals D over time. So D means distance in this case, so it's distance over time. So if it takes you 2 hours to drive to Dallas, how fast are you going? Well, you better get out of my way because you're driving 50 miles an hour, and I want to get there quicker than that. So 100 miles divided by 2, it's taking you 2 hours to get there, would be 50 miles an hour. So that's your velocity. Average velocity is like finding the average of anything else. Average velocity would take different quantities and divide it by the number of quantities you have. So I like to use the example of test questions. So this semester we're going to have one test per chapter. We have test over chapter 1, test over chapter 2, test over chapter 3, test over chapter 4, all the way until we run out of time this semester. So we'll have as many tests as we can fit into this semester. So let's say we have, just to make it easy, 5 tests, right? So you'd take your grades off of each one to find your average. You'd take your grade off of each one of those tests and you divide it by 5 to find out what your average is for the semester. And with velocity, average velocity is the same thing. So you would take your starting velocity, or your original velocity, that's your VO according to Bushong, and add it to your finished velocity, and then you divide the two by 2. So in this case, it would be 50 plus 10, or 10 plus 50. Dyslexia kind of messes with me. 10 plus 50 divided by 2, so you've got 60 divided by 2, you'd be 30 miles an hour would be your average velocity. Acceleration is the rate of change of velocity. So it's the difference between your original velocity and your final velocity divided by the time it took to make that change. So your average, what you would have there, is a little bit different than finding your average from before. Your acceleration, rather, would be your ending velocity, VF, finished velocity, minus your original velocity, divided by the time it took you to make that change. So again, you're going back to your analogy of driving to Dallas. So if you're driving to Dallas and you're going, you get stuck behind a tractor and the tractor's driving 20 miles an hour. It happens. This is East Texas, right? So you're driving 20 miles an hour behind this tractor, and you go to pass him. That's where that will come in. How long does it take you to go from 20 miles an hour to maybe 40 miles an hour to get around the tractor? So your finishing velocity would be 40 miles an hour. Your original velocity would be 20 miles an hour. How long did it take you to get around the tractor? So maybe it was 5 seconds. So that would be your acceleration. We're going to talk about acceleration of gravity here in a minute. And acceleration of gravity is 9.8 meters per second squared until you reach terminal velocity. And terminal velocity at sea level in the atmosphere here is somewhere around 250 miles an hour. So I'm going to have a question for you here in a bit that I'm going to ask, and I'm hoping that I get some responses on YouTube about why it is that we can actually exceed that terminal velocity. So we have acceleration. Well, we just talked about that. So what does any of this mean, and why do we have to study it? Again, I don't know that this is going to be on the registry, but it's good information to help you to understand how it is that X-rays are created. So I've got all this information in there. To make X-rays, we create high electric potential. Stop there. High electric potential. What does that mean? Well, high electric potential, again, we've got that P there. So electric potential, kVp, potential difference between cathode end and the anode end of the X-ray tube. So we create this high electric potential difference in the X-ray tube. That's your kVp. That difference is used to accelerate the electrons from the cathode to the anode. The acceleration ultimately controls the terminal velocity of the electrons, carrying with it kinetic energy that we've talked about before, and we'll talk about again at the end of this chapter, that has to be lost in the anode. So we accelerate the electrons from the cathode to the anode, and they smack really hard into the anode, and they slow down immediately and very rapidly. So they lose their kinetic energy, and that energy has to go somewhere. According to the law of conservation of energy, that energy has to go somewhere. So what happens then is that they lose that kinetic energy, and what we get is the creation of an X-ray photon, but more likely the only thing that's going to happen is it's going to increase the heat on the anode itself. Is the electron's going to return into the circuit, and it's going to complete the circuit. So this BRIMS here is something that I'm going to explain later on. It's one of the ways that we create X-ray photons, and the BRIMS stands for a shortened version of a German word called Bremsstrahlung. And you just have to look that up. I'm not going to try to spell it right here. But it's a long word, so we shorten it to brims. And what bremsstrahlung means is breaking or slowing down. So when we create X-rays, there's two different ways that we're going to create X-rays. And one is just strictly due to the loss of kinetic energy when the electron slams into the anode and slows down very rapidly. Breaking means slowing, brems means slowing, and so X-ray creation, a lot of our X-ray creation, statistically, according to the textbook, 95% of our X-rays are created in that manner. They slow down really quickly, and most become heat, but about 15%, or I'm sorry, about 85% of our X-ray photons that are created in that way. So now we're going to pick up with Sir Isaac Newton and his three laws of motion. And Isaac Newton was a brilliant individual. He's accredited with these three laws, and he's also a lot of people say he's a gravity guy. He described gravity and described the acceleration of gravity and all that. So yeah, he's the gravity guy. So his three laws are three things: inertia, force, and action reaction. So we're going to talk about each one of those individually. Inertia means resistance to change, and all things have inertia. So what you may have heard this referred to as a body at rest tends to stay at rest unless it's acted upon by external force. A body in motion tends to stay in motion, again, unless it's acted on by external force. So body at rest stays at rest, body in motion stays in motion. And that's a little bit hard to wrap our minds around, and it certainly would have been hard for somebody in the 1600s to wrap his mind around and to sell that to the world. Because let's say, I wish I had a different camera, but if I were to put this on my hand and move it, it's going to come to a stop, right? So it's in motion, but it comes to a stop, right? So it's just a napkin, and it comes to a stop, right? So how can I say that a body in motion is going to stay in motion? Well, think about what is going on with this thing. So it rolls across my hand, and what we've got is friction on my hand. We've also got gravitational pull on this. Even though my hand's off the ground, it's still gravitational pull pulling this down into my hand. So we do have an external force that causes it to not remain in motion. So where does this really apply? Well, if you look at the planets and you think of the vacuum of space and how satellites work, satellites go around and around the Earth, and there is a decay to their orbit, and they eventually fall back into the Earth if they don't have something to keep them in orbit. But for the most part, since they're mostly outside the gravitational pull of the Earth, where the gravitational pull isn't so strong, they'll stay in orbit for a very long time. So in the vacuum of space, if you were to send a rocket ship out into space at 10,000 miles an hour, and it gets outside of the gravitational pull of anything, it will remain going in that direction pretty much indefinitely until something hits it. It's going to get into the asteroid belt, and it's going to have a very bad day. But until that happens, it's going to go in a straight line until something acts on it and moves it in a different direction. So if, though, you get something out into space and you have it sit perfectly still, it's going to remain there indefinitely until something hits it and it goes off into a different direction. So a body at rest will remain at rest, and a body in motion will remain in motion unless something is acting on it with external force to cause it to change. So if I roll a ball across the floor, friction and gravity are going to cause that ball to stop moving. But if I could throw it hard enough to get it outside of the gravitational pull of the Earth, it'll go on forever. So it applies to things outside of our atmosphere, applies in the external forces that would affect us inside the atmosphere would be the gases, the liquids, the solid, gravitational pull, and things like that. So force is just a mathematical equation. It's pretty obvious. Force is equal to mass times the acceleration of that body of mass. So now, though, our mathematical equations are getting to be a little bit more complicated. So we've got compound equations. So acceleration, remember what acceleration is. Acceleration is the final velocity minus the original velocity divided by the time it took to make that change. So acceleration is change in velocity, right? So force is a mass times the acceleration of that mass. So the higher the mass, the higher the force. The higher the acceleration, the higher the force. So it's measured in newtons, and it includes weight. That is your mass times your acceleration of gravity. Newtons, pounds, or stones would be your unit of weight. So Newtonian physics at work, we've got acceleration of gravity, we've got action, reaction, we have force. So this, I'm going to leave you with these links, and I'll post the link here into the comments section. I don't know that this will post since it's outside of YouTube, but Felix Baumgartner, back in 2012, I think it was, he took a helium balloon all the way up to the edge of space. So I'm tying a lot of stuff together here. He took a helium balloon all the way up to the edge of space. It seems like it's 112,000 feet or something like that. It was way up there. And he had a spacesuit on, and the helium balloon had a capsule hanging from it. And so what he did was he got up to altitude, and he opened the door of this capsule, and he stepped out, and he stepped off the platform, and he started a free fall that took almost 5 minutes for him to get to the ground. Now, you got to think about that. I don't know if anybody in the class has been skydiving, but generally speaking, if you go skydiving, you've got seconds before you have to pull your parachute, before you get yourself in trouble. This guy free fell 5 minutes, almost 5 minutes. It was 4 minutes, some seconds. And it was such a far fall that he broke the speed of sound. So speed of sound is different in different medium, right? So the more dense medium, if you're in the ocean, speed of sound is about 1,000 miles an hour. And the less dense the medium, the slower speed of sound. But he still got up to like 800 miles an hour. So he was traveling really, really fast. He's got the record for the fastest free fall. He's got the record for the fastest unassisted time. So he wasn't in an airplane or anything like that. It was a straight free fall. But wait a minute. I said just a minute ago that terminal velocity is around 250 miles an hour. So what gives? This guy's going over 800 miles an hour and he breaks the speed of sound in a free fall. So that's question number one. Question number two is that he's still alive today. If you were to be traveling along at 800 miles an hour and you pulled a ripcord on a parachute, and that's how he got back to the ground, is he parachuted back to the ground. If you pull a ripcord on a parachute while you're doing 800 miles an hour, you're going to get ripped in half. It's just going to tear you to pieces. You're not going to survive it. But he's still alive today. So how did he get up to 800 miles an hour? That's question number one. And how is it that, and it's closely related to question two, how is it that he was able to pull his ripcord and float safely back to the earth and it didn't kill him? So those are my questions for you today. Those are your critical thinking questions for today. I'm going to pull up this recording there, so hopefully it will load, and I will finish this chapter out. We'll probably have a test week after next, maybe on the 20th, September 20th, and it's just going to be over chapter 2. Again, you're not going to have to work these formulas. You have to know the components in the formula, and you have to know what from a description, what the formula would look like. For example, if I said the I don't know, the distance you traveled over time would describe what mathematical formula, and that would be velocity. Okay, so you have to know the components, and you have to be able to pick the formula out of a description. So, and they're all going to be multiple choice questions. I give multiple choice tests almost universally. There's sometimes we'll give, a fill in the blank. So we're going to pull it up there. Answer the questions in the comment section. And if you found this helpful, or if you've found this at all entertaining or whatever, please consider giving it a touching the thumbs up button. If you're not one of my students, please subscribe and share with the students in your class. Thank you very much.